All right, welcome back to CE 529. We're getting close to the end now. And I do have a travel coming up next week, so I won't be here Tuesday. And I'll make some alternative arrangement, but we will not meet here. Either it's going to be a recorded class, and if I can make it work, there might be a guest speaker, but it's going to be virtual anyway, regardless. So no class meeting here in the classroom. Lab, lab would be open because I know you all have to catch up. Gotten some emails about the senior design, which I was expecting, which is fine. So if you need to take more time on working on the lab, that's okay. I'll update the due dates as long as you're able to spend some time on it and do a good job with it. Should be okay. So I will extend those deadlines. We can talk about that in the lab today. And then what we have to do is, like, in terms of lab assignments, I just have a couple of things left. What I want to do is I want you to now work off of, like, the data that we get out of vSim files, the trajectory files that we get from vSim. So now we're going to work on the surrogate safety assessment model that we learned about. We're going to try to assess that safety using the trajectory data that comes out of vSim. So you're going to essentially take your freeway network, you're going to download the trajectory file, and you're going to process that through SM. So that's one lab assignment that's left. And then the other one would be what we're covering today, trying to apply an application of that. So I'm going to give you some travel time data for vehicles for that you can now then apply the theory that we're learning here to that real world data, to that, not real world data, but the simulation data that comes out of PTV vSim of a real network really. So that's going to be the sort of the remaining plan. So we don't have a ton of things left concept-wise. And we will cover, so we'll start, like, your final exam, you'll start with the lane change estimate of delay due to lane changes. Then we're going to talk about the shockwave and queuing theory, talk about the surrogate safety, and talk about this two fluid theory. So these are the topics that you will have for your midterm number 2 and the final during the dead and during the dead week. And then if you decide to take the final, we'll go from there. Okay, so two fluid theory. So let me sort of contextualize it for you. We talk a lot about macro level models when we are thinking about freeways, uninterrupted flow, right? Uninterrupted flow means no signals, no stop sign. Vehicles are not supposed to stop. They're supposed to keep moving. And we do a lot of that in our, for uninterrupted flow. So we have models like, if you think about it, Q equal to K times V, right? So Q equal to K times V, flow equal to density times the speed. That is a macro level relationship, but it only applies to uninterrupted flow, okay? Not to the interrupted flow that you might see on surface streets. Okay, so this is all for uninterrupted flow. Okay. So this two fluid theory gives us a way to conceptualize the traffic at a macro scale, for interrupted flow, for urban streets. So for urban surface streets, what are some of the macro level relationships look like? Can you actually define some macro level relationships? Now, why is this important? Because throughout this class, this is a modeling class, right? And one important aspect of modeling is to be able to see the congruence between what happens with the individual interactions versus things that you can measure in the field. Now, obviously, the technology is evolving. And what we're going to have our guest speaker talk about on Thursday is that as the technology evolves, we are now able to get video data and trajectory data and be able to observe all of those things in real world. But that technology still remains somewhat expensive and somewhat cumbersome to implement, right? So, but being able to see the relationship between the micro level interactions between individual agents or individual vehicles or individual users, and then translating them into macro level observations is useful because macro level things are something that you can more readily validate, right? You can measure the travel time from point A to point B rather easily. You can figure out what percentage of vehicles are stopped at any given time more easily, things like that. So if you can, so this is what we are trying to do is we're trying to see if we can come up with a theory that explains the flow on surface streets like that is done by, maybe not quite exactly the same way, but like you could do for Q equal to KV. All of our highway safety manual relationships are based off of that. But what if we have a surface street network, like what you might see in downtown San Luis Obispo, for example, right? On those types of network, are there ways of defining the relationship between the vehicle's movement, vehicle speed, stoppages, travel times, all of that? Okay, so that's what we are trying to do with this theory. So the theory is called the two-fluid theory, and the two-fluid stands for, what do we mean by two-fluid? The two-fluid means that our vehicle composition as a whole is going to be made up of moving vehicles and stopped vehicles. So those are sort of my two-fluid. One fluid, like one part of the fluid that's stopped, the parked cars or not parked cars, I'm sorry, the cars that are stopped in traffic, and then the cars that are moving in traffic is my other fluid. So those are the two fluids that I'm talking about. Yeah. The two-fluid model provides a macroscopic measure of the quality of traffic service in a street network, which is independent of concentration. Okay, so when we say concentration, here they're using the term concentration, and they're talking about density. They're talking about density here. Okay, so when it's a concentration, this is about density. So that analysis is based on two sets of assumptions. Okay, two sets of assumptions, and I'm going to zoom in here a little bit. Okay, so what are the two assumptions here? The average running speed in a street network is proportional to the vehicles that are moving. Okay? The average running speed in a street network is proportional to the fraction of the vehicles that are moving. Does that assumption make sense? So read through that and tell me, does it make sense or does it not make sense? If there is a network, street network, and more vehicles are moving in that network, then the average running speed would be higher. But if there are fewer vehicles moving in the network, the average running speed would be lower. And that makes sense. If there are more vehicles moving and fewer are stopped, then you would get that, and that makes sense. And then the second one is called the ergodic assumption. This is interesting too, and this could take some time to think through. The fractional stop time of a test vehicle circulating in a network is equal to the average fraction of the vehicle stopped during the same time period. Okay, so this is a little bit more critical assumption here. More critical assumption. Yeah. So if you want to estimate how many vehicles at any given time are stopped, like let's say you observe the network for 30-minute period or 1 hour period, and you want to figure out how many vehicles are actually stopped on the network, you can do that using a test vehicle. You can have somebody drive around a test vehicle for 1 hour, try to follow cars or whatever way, just normally drive with the traffic on that street network. And then if you say the test car had to stop 30% of the time, let's just say, like they drove around for 1 hour and 30% of the time their speed was 0. Okay? So what they're saying is that one assumption you can make is that you can say that for that 1 hour period, if you look at the aggregate vehicle distribution, 30% of the vehicles would be stopped at any given point. Okay, it's not an obvious assumption, but it does make sense to me. And I want you to think about it a little bit and tell me if that also makes sense to you. So we are doing two things. We're saying that, hey, I can't quite observe how many vehicles are stopped in my network. I can't observe that. I don't know. Like, the network might be, even a small network, even if you model like, 2 by 2, 2 square feet, or 2 feet, a 2 mile by 2 mile network, that'll give you, like, if you look at the road network length, that'll be about 150 miles or something, right? Pretty, I mean, give or take. Like, I know these numbers right now. There's talking about a project about simulating downtown Atlanta where we're doing that. So that is a small network about like, maybe 4 square mile or something, or even a little bit less than that. And we're talking like simulating 140 miles of roadway just within that segment, right? So it could be a very large network. It's hard for me to observe using aerial pictures or whatever, like continuous aerial pictures, to figure out what percentage of vehicles are stopped at any given time. Very hard for me to do that. But this is the assumption I can make, is that if I drive around in a test vehicle and try to follow cars during 1 hour period, as long as the conditions are not changing rapidly, they're sort of steady state conditions, I could say that if I had to stop as a test car driver, I had to stop 30% of my time. It's a good assumption or a good estimate that at any given time, if you observe, 30% of the cars would be stopped. Okay. Can you repeat that assumption in your own words, all of you? Make sense? Does it make sense? Right? So we're trying to figure out from the test car, we're trying to go to what are the overall network conditions. Yes, please.
Sorry, this is like a dumb question, but I'm curious about
no
the
dumb questions.
Assumption that the running speed in the network is proportional to the why is that like listed as an assumption and not just like something that is objectively true? It seems like that would be easy.
It's an assumption because, the average running speed, it could be, in some cases, it could be that if you have fraction of vehicles that are moving, it might not be directly proportional. Like, so think about this. So the question is, the first one, why is it an assumption rather than sort of an objective fact, right? So average running speed in a network is proportional to the fraction of vehicles that are moving. In some cases, that assumption could be violated if you have network, a small portion of the network where, let's say you have sort of like a very big concentration of let's say what do you call them? The coordinated signals, right? Coordinated signals, average running speed or speed network is proportional to the fraction of vehicles that are moving. Over a whole time period, if you only observe, like when the signal is red, you might see the vehicles are stopped and nothing is moving because they are sort of moving in a continuous wave or something. So there are pieces of the network where these assumptions might get violated. But what we are saying here is that I think this could be so our network is of reasonable size, that there are like sort of maybe even competing traffic waves going. So maybe there are 2 or 3 parallel streets that have all sort of these signal timing, and you're observing that large enough network for a large enough period where, yes, this is almost as close to an objective fact, but there could be, like, if you observe only like a little piece of the network, you could have a situation where this assumption might get violated because you're not observing it for long enough, or you're not observing a large piece of the network. You're observing like maybe just one green wave type street corridor. Okay, does that make sense?
Yeah, I think so.
Okay. Yeah, we can talk more if there are more questions later on. So, but yeah, so this is again an assumption here. And now using both of these assumptions, now we can start to build sort of a mathematical model here. So this is the first assumption. So if you take the first assumption, this is what we are going to assume, that VR, the running speed of a network, VR, equal to VM, which is VM is the average maximum running speed. So VM is the average maximum running speed, times FR. FR is the fraction of running vehicles, raised to power n. Raised to power n. And we are saying VM and n are parameters of this model. So you can define those values to be constant values for a given network. So you can say, so like if I simulate downtown San Luis Obispo network or downtown Atlanta network and whatnot, I could assume these to be, what we call the model parameter. So VM is a model parameter, N is a model parameter, but VR and FR are sort of the variables in the model. Okay? So you can define VM value and N value for City of San Luis Obispo network. On any network that you're analyzing, they typically tend to hold constant values. And so that's why N is an indicator of the quality of service in the network. And we'll come back to this, what this N might mean, okay? So N, for now, we'll just call it some kind of an indicator of the quality of service in the network, okay? Now, if you were to say, okay, I want to find my average speed. Okay, so you have fraction of vehicles that are running is FR. So, and then let's call them FS being so FS is the fraction of stopped vehicles. FS is the fraction of stopped vehicles. So if I want to find the network's average speed, does this make sense to you? If I want to find the network's average speed of movement is VR times FR plus VS times FS. So VR is the fraction of running vehicle speed, average. FR is the fraction of running vehicles. VS is the stopped vehicle speed, and FS is the fraction of stopped vehicles. Okay? But what does that mean? What is the average speed of stopped vehicles? 0, right? So they're stopped, so they're not moving. So basically you can say, okay, this term doesn't really exist because VS is 0. The speed of stopped vehicles is 0, right? So I could just say the average speed on the network over as a whole could be defined as VR times FR, okay? So that gives me this equation. If I plug in V equal to VR times FR, so if I take this and combine it with this one, VR times FR, so I can just replace VR with VM times FR raised to power N. So I'll get this equation. Does this make sense? V equal to the average speed of the network is VM times FR raised to power N plus 1. I can also write it down on the board just to make it very clear. So my equation then is the average speed on the overall network would be VM times FR raised to power N plus 1. So this is sort of my equation, is what it becomes. So that's equation number 630. In your book here is equation number 630. V equal to VM times FR raised to power N plus 1. Everybody clear on how we got to equation 630? Okay, good. So then, obviously, FR plus FS, fraction of running vehicles plus fraction of speed stopped vehicle should be 1. So I could just replace this FR with 1 minus FS. So I'll get V equal to VM 1 minus FS, fraction of stopped vehicles raised to power N plus 1. And that gives me equation number 631. So equation number 631 is easy enough because I could just say V equal to VM times 1 minus FS raised to power N plus 1. And all we did was replace FS with 1 minus FR. Or sorry, FR with 1 minus FS. So we replaced FR with 1 minus FS. Yes, please.
Why did you get the FR plus FS equal 1?
So this is, remember, FS and FR are defined as, so question is, how did we get FR plus FS equal to 1? FS is the fraction of stopped vehicles and FR is the fraction of running vehicles. It's a fraction, right? So fraction of stopped and fraction of running, if you add those two fractions, you get 1. That accounts for all of the vehicles in your network. So those fractions should add up to 1. Okay. Now, so here are some boundary conditions for this. The boundary condition would be if FS is equal to 0, if all vehicles are moving all the time, you get V equal to Vm. And when Fs is equal to 1, V will be equal to 0. So those boundary conditions they make sense, right? If everybody stopped, then your average speed will be 0. And this equation does satisfy those conditions. If Fs is equal to 0, V will be equal to Vm. If you plug in Fs is equal to 0 in equation 631, you get V equal to Vm. But if you plug in Fs is equal to 1, meaning everybody stopped, then you get the average speed of 0. Now, one thing that we could do with this is that we could represent these. We could represent these in the form of average travel time rather than speed. Okay, the average travel time rather than speed. So this is where this comes in from. The relationship can be expressed in terms of average travel time rather than average speeds. Note that capital T represents the average travel time, T, the running time, and the stop time. So if you look at the total travel time, so if you're traveling through the network, your total travel time would be made up of the time that you're stopped and then the time that you're running. Okay? So if you're if you're traveling through a network of surface streets, the average travel time would be equal. Your travel time would be made up of two components: when you're stopped, when you're moving, and those are your TR and TS. TS represents the stop time, okay, and T represents the travel time, and TR represents the running time. So there are three items: capital T, TR, and TS. Okay, so you got three of these things, and what you can do is you can start converting those into travel time. And one thing we are also saying is that anytime I say that travel time in capitals, they are defined by per unit distance. Okay, so they're directly reciprocal of speed. Okay, so it's travel time per mile, travel time per mile, travel time, running travel time per mile, and stop travel time per mile. They're all defined per unit distance. They're all defined per unit distance. So you could say that your T is basically 1 over V, the reciprocal of the speed directly. Travel time per mile is essentially reciprocal of speed. TR is equal to 1 over VR, and TM is equal to 1 over VM. Okay, but TM now, the only thing that changes now, that when you do the reciprocal, remember VM was the maximum possible speed. So TM will be minimum possible travel time through the network. Okay, so that's the only thing, because you're doing the reciprocal. The maximum travel time becomes average minimum trip time per unit distance. So this is something that we've derived just from the first assumption. We haven't even touched the second assumption yet. Okay, we haven't touched the second assumption as of yet right now. Just based on the first assumption that your fraction of running speed will be equal to, or will be proportional to, fraction of running vehicle. Okay, and we'll come back to what these N and TM means in a minute too. Now, let's think about this, the second one. Now we're getting into the second assumption. The second assumption of the two-fluid model relates the fraction of a test vehicle circulating in a network is stopped to the average fraction of vehicles stopped during the same period. Okay, now we are applying the second assumption by saying that you can generate this FS. This is hard to do though. For the whole hour, what percentage of vehicles were stopped? It's very hard to figure out, because then you'll need information of all the vehicles that might be moving through the network during that 1 hour observation period that you have. This is very hard to do. So that's why we're making an assumption here. And actually, give me Fs is equal to just Ts divided by T. Ts divided by T, which is, if you're traveling as a test vehicle, how much travel time did you spend stopped? How much time were you stopped during a mile of run? Divided by the travel time T, the actual travel time that you spent traveling that distance. Okay? Is that, so now I'm going to go back real quick to the second assumption. And I want you to be able to see how equation number 632 follows from this assumption. The fractional stop time of a test vehicle circulating in a network is equal to the average fraction of the vehicle stop during the travel time. So this is what we want to find out. Average fraction of the vehicle stop during the same period. So this is what my FS is. This average fraction is what FS stands for. And now I want to find FS is equal to, and I'm going to say that TS divided by T is my FS. So that I'm going to say, okay, I can derive that FS value using what a test vehicle is doing when they're moving through the network. They are, stopped for certain times, they're moving for certain times. And based on their behavior, I can capture what's happening overall in the network. Okay, so this is the assumption. Does that make it clear? Like you see that how equation 632 is derived, how equation 632 is derived from the second assumption. Okay, so this is the key one. Okay, and then this is obviously this has been proven analytically if you have a large sum network. And then this is what we call, as I said, ergodic assumption or ergodic principle embedded in the model. So now what you can do is you can take this equation 631, you can take this equation 631 and write that in terms of travel time. Yes, I can replace what we had in equation 331, the speeds. I can represent them in terms of a travel time of a test vehicle. And this is what that looks like. I can replace the left-hand side with the T, Tm, okay? 1 minus Fs times negative n plus 1. Okay, so there is a negative sign over here, which is kind of hard to see, but I hope you can still see it. So my equation becomes, I'm going to write that down on the board just in case it's not very clear. So T equal to Tm 1 minus Fs raised to power negative n plus 1. Okay. And what I want you to see is this is equation 633. And then the 632 equation, remember, was Fs equal to Ts divided by T. Remember? My equation Ts divided by T was my Fs. Okay. So this is equation 632. Please take a minute to make sure that you can derive equation 633 from 31 and 32. Take a minute maybe to derive equation 633 from 631 and 632. And obviously we are converting V being, so this V will become 1 over T. Vm will become 1 over Tm. And Fs is Ts over T. So all of, and I haven't changed the Fs yet, but we will ultimately do that. So if you replace, actually it's not using 632, I'm sorry. It's actually just replicating this travel times or replicating the speeds in the form of travel time. Okay. Make sense? Questions? So I'm just going to V equal to 1 over T, Vm equal to 1 over Tm. Place those here. And then this is what you end up getting. Everybody good with that? Just replacing V to be 1 over T. So all you're doing is V equal to 1 over T. Vm equal to 1 over Tm. And then simplifying that to get this equation 633. And then next equation will incorporate 632 now. In the next set, we'll take 632, which was nothing but Fs is equal to Ts over T. So we'll take that. Fs is equal to Ts over T. And then I plug that in there. Ts over T. Capital T equal to Tm times 1 minus Ts over T, negative n plus 1. And then you could say that your overall travel time per mile will be just TR plus TS. Your aggregate travel time per mile will just be TR plus TS. And then you could simplify that to solve for TR. Okay, so you could replace this T with TR plus TS. Or you could say, because you want TR and T in the final equation, because I want TR and T in the final equation, I can replace TS is T minus TR. I can replace TS with T minus TR because your total travel time is just the sum of running time and stop time. TS is equal to T minus TR time. And I can simplify that into this equation where I can derive TR is equal to Tm raised to power 1 over n plus 1, T raised to power n over n plus 1. So let's take a minute maybe to see if we can make sure that we can derive this from equation 634 to get to 635. All you need to do is just replace TS with T minus TR. Let's take maybe 2 minutes to see if we can write that. If you can't, then let me know if there's any questions about this. So let's go ahead and derive from this equation the derivation that we're trying to work out is, we know this, T equal to Tm 1 by Ts over T. And now you don't want, remember in your final equation, in this equation right here, in this equation, there's only TR and capital T. So you don't want TS. So you can replace TS is equal to T minus TR. So if you take that and you start sort of rearranging the terms that you have, you will be able to get to the equation number 635. The TS is equal to T minus TR. These are the equation I'm trying to manipulate. T equal to TR. So we take away TS and say it's T minus TR. Trying to work out the derivation. It's not that hard, but we will cancel out here. Is that the equation or is it slightly different? I'm trying to derive TR from here. So I'm just going to try to solve for TR. I'm just going to make it reciprocal, so I get rid of the negative.
Should it be 1 plus TR over T?
1 plus TR over T? No, but I'm taking T as the... No, I have 1 here, right? So when I do this T, doesn't T cancel out?
I guess like where's the parentheses?
This one? So TR over T, is this the step that you see the point? Yeah. Yeah. So this is 1 minus Fs, right? It was 1 minus Fs, I replaced that with Ts over T. 1 minus Fs was Ts over T.
Okay, I guess I'm just a little confused how to get from the third.
From this to this?
From what you're pointing at now.
Okay, from here to here. So yeah, I'm dealing with this parentheses right here. Just dealing with this, and then I'm saying, okay, so this is one term, this is one is another term. So my LCM for this is, LCD is for this is T. So T minus T plus TR, that's all I end up with.
Okay.
Okay, so there's a little bit of algebra here, but hopefully you can all, given enough time. Okay, but this makes sense, right? So I got Tm, T over Tr is to n plus 1. Is that now what I have here? But I want to find Tr though. Okay, so if I want to find Tr raised to power n plus 1 equal to m raised to power n plus 1. There's something here that I'm missing. Is there another n anywhere? All right. So you should be able to get Tr equal to Tm over 1. Yes, Tm power will be correct. But what's off about this? What's that? Oh, there's a T on the left side of the equation. That's exactly. Okay, so there's a T on the left side of the equation that I was missing. So yeah, given enough time, right? So I need to figure that out. So then T times Tr raised to power n plus 1, Tm T raised to power n plus 1. And so if you were to solve this, so I go back up here. So if you want to write the equation for Tr, this is what we're doing. Tr equal to, so just 1 over n plus 1. So Tm raised to power 1 over n plus 1. And then this is T raised to power n plus 1, and T is also here. So this will become T raised to power n. No, I can probably just say this for now. Does this make sense? So if I just want to write Tr raised to power n plus 1, I can divide both sides by T. And this becomes Tm, and this becomes Tm, T raised to power n. Okay? And then I can figure out what Tr is going to be. Which is the equation number 635 that you have. What I'll do is I'll take a picture of this if you're just for the recording purposes. I'll take a picture of this and post this, what the derivation looks like to go from 634 to 635. But questions about this? So now we've gotten from 634 to 635. I will post a picture of the board with the lecture here at the end in our recording. So once you figure out Tr, you can again write this in terms of Ts, because Ts is simply T minus Tr. So I can go back to Ts. It's just capital T minus Tm, 1 over n plus 1, T raised to power n over n plus 1. Okay, because Ts is nothing but T minus Tr. T minus, this is the equation for Tr that we got from 635. So we got 636 here. Now the good thing about this is that if you take this Tr equation, and do a natural log of this, okay, if you do a natural log of this Tr equation, you can what we call linearize an equation. Okay, because there is obviously this is an exponent equation, but by taking the log of this equation 635, we can linearize it in this way. So I'm going to go back a little bit up here so you can see both. So take a look at 635. Take a look at equation 635 and see how am I linearizing it by taking the log on both sides. Okay, so the natural log of Tr on the left hand side, 1 over n plus 1 ln Tm plus n over n plus 1 ln T. You'll see that. Just took the natural log of equation 635. This is what I ended up with. Okay, now this is useful. But first, before we get into the how this might be useful for us to evaluate an urban network, what I want to talk about is, does this make sense, or Are there questions about this? Like, we just took the log and we ended up with this equation. Now, this is a great linear equation because remember I told you TR and capital T are your variables. So they're looking at the relative running time and the average travel time that you would have. Right? And that will depend on how much you have to stop and all of that. But these two variables, if you can figure out these two variables for a network, for multiple vehicles, if you observe them for multiple vehicles, and you can get a sense of TR and capital T and run a regression model, a linear regression model, right? Just a simple least square regression model, you can get the linear line fit in the form of y equal to mx plus b, right? Or you could say, in statistics terms, beta naught plus beta 1x. You can get an equation into form of y equal to beta naught plus beta 1x. Okay, where x is ln(t), y is ln(tr), and then when you fit that linear equation, the constant of that equation becomes this term. The constant of that linear equation becomes this term. And then the coefficient of that equation becomes this term right here. Yes. Yeah, so I'm coming to that. Yes, that's my next thing. What does n represent really? What does it mean to have a higher value or a lower value of n? And that's what's most important here. But before we get to that, what I want to make sure is that if you have some data on travel time per mile of a vehicle and running time of a vehicle as well, okay, you can fit a standard least square linear model with using even Excel. And then you can look at the constant term of that equation and you'll get this parameter, 1 over n plus 1 ln Tm. And if you look at the coefficient of ln T on that equation, you'll get n over n plus 1. So you can get the value for n and Tm for any network of your choosing if you are able to fit that linear regression between ln T and ln Tr. ln Tr being your dependent variable, ln T being your independent variable. Okay, so what is this relationship exploring? It's exploring how much of your travel time that you're spending per mile you're able to be in a running situation. Okay? Now, once you figure out your n and Tm value, so for example, this is a graph where they figured out the n and Tm value using 566 data points. So what they did here was they had a test car driver. They had that test car driver drive around in the network, following vehicles in a more or less sort of conservatively just follow like in a normal way. Don't try to obviously get into collision or anything, but try to follow a certain vehicle that's right ahead of you. Don't leave too much gap so that somebody could come in, but be safe, obviously, and just try to follow around. And every 1 mile of travel, and then if that vehicle left the network boundaries, they just started following some other vehicle. Okay, and then that way they followed total of 566 vehicles at different times. It's 1980, 81, 82, 83, all of that. Right? So this is older data, but we have done I've published some work on this with like, I think 2010 data, 9-10 data as well. But we found similar results. But this is good because now what they did was they regressed the travel time and the running time, and they're showing some different chart here, stop time and travel time. You can get that from there as well. But they applied this method by taking the log and estimating the value of n and Tm And they found 1.11 for TM and 1.03 for M. Now let's think about these values a little bit. What does TM represent? TM represents the minimum travel time that you could have per mile. Okay. Remember, VM was the maximum speed. So the corresponding value TM would be the minimum travel time. So that means they found that if you never have to stop at all, you can travel 1 kilometer distance in 1.11 minutes. That's what TM represents. You never have to stop. You could travel that distance in 1.11 minutes. And it's possible that they never actually had vehicles that had that low of a stop. All they're doing is basically they're extending. And this is not this line because that line would be logarithmic scale. But they basically extend that fitted line back to the y-axis to figure out what would be happening if the stop time went to 0. How much time would you be spending to travel 1 kilometer? So they said 1.11 minutes. Yes.
So is this modeling like the metropolitan area? Or
yeah. So this is modeling. Texas? Yeah, that's a great point. So they are modeling not the whole freeways or anything. This is just the downtown Austin network. Okay. So they're modeling what was happening in downtown Austin and what does the network look like? Well, how much speed you had. So this is a little bit less than 60 kilometers per hour speed, so which is pretty high speed actually, right? And then now when they started doing the studies, if you look at like the original studies here, they think that they wanted to minimize this time. They wanted to minimize this time. They thought 1.11 minutes per kilometer because they thought it'll be nice to have vehicles moving fast. But I don't know if that's true anymore because maybe on the urban surface speed, maybe we are okay with TM actually being a little bit higher. Okay. So maybe we can slow down the vehicles through downtown and move them a little bit faster. That gets me to N value of 1.03. Now this N value represents how resilient your network is to disruptions. As you add more stop time. So if you look at this N, it's N over N plus 1 times L and T, right? If the value of N goes up, this N over N plus 1, so if value of N goes up, basically that means that as my stop time increases, my overall travel time increases right along with it. So what N tells me, N, you can think of N as a measure of resilience, N can be thought of as a measure of resilience to adding more traffic. What happens to your travel time as you add more traffic? And I will probably take a few more minutes to describe this a little bit more in the next class. And then we'll sort of wrap this discussion up because I do want to talk a little bit about N, and then I'll talk a little bit about what they found in different cities, and then and I also talk about what kind of problems you can expect in the exam from this, and what's going to be your lab assignment as well. So we're gonna talk about this, wrap this discussion up in next class. We'll go from there, and then yeah. Thank you very much. I appreciate it. I'll see you in the lab.